Hey, welcome back. We're going to do a second day on hypothesis testing for proportions with one proportions. Kind of reiterate some of the things that we've done and talk about a couple other situations you might see. So, um, do you know the recipe for constructing a hypothesis test without looking at your notes? There's your question. Can you do it? See if you can. If you can't, make sure you get these written down because here they are. And I wish it was a little bit smaller. But here it is. All right, number 1 and 2 go together. State the parameter and write the hypotheses. Got to do that. Name the test. So right now we're doing with one proportion z-test. Check the conditions, same conditions we've been checking, and find your z. So this part right here, write your formula, plug and crunch. That deals with finding a z value that fits with whatever the situation is. In this case, we're doing p hat minus p because we're dealing with proportions over the standard deviation for a sampling distribution of proportions, which is right there. Once you get that, you can go to your normal curve, look at your z-table or normal CDF and find the p-value. And once you're done with that, make our conclusion. So we want to compare it to whatever the alpha is. If it's lower, then it's enough evidence to reject the null if it's lower than the alpha. And we can say we do have convincing evidence of the alternative hypothesis. If it's higher, then it's a fail to reject. We don't have evidence to say otherwise. So real quickly, if this is our formula for finding a z, why do we have to find, like, actually do each condition? Like, what's the point of it? And it all has to do with the parts of this formula. So that top part, when we're doing like p hat minus p or p naught, whatever the population parameter is, that has to do with generalizing. We're dealing with comparing a population and a sample. And in order to do that, we have to have a random sample from the population. So that's where that comes from. The large counts condition, the n times p, n times q, we need that in order to know that it's a normal distribution or approximately normal. And that's where, if you want to use z-scores, you have to know that it's approximately normal. So that's that part right there, if we can even use this formula. And then the third one, the 10% condition, when we're dealing with sampling distributions, whether it's proportions or means, we need to know independence. And normally we're sampling without replacement, so it's not technically independent. And this, based on the size of the sample compared to the population, you can assume independence. That allows us to use that part. Okay? So there's a recap of those three things. Now, I want to get into an example, and it's going to be a little bit different. Actually, before we do that, I want to shout out to this. We've talked a little bit about the combination of, or the connection between confidence intervals and hypothesis tests. There is a link between confidence intervals and two-sided hypothesis tests in particular. So a 95% confidence interval does give you an approximate set of proportions, population proportions, that should not be rejected by a two-sided test at the 0.05 level. Any p-value outside of that interval should be rejected as implausible. So if you are actually wanting to look not just at the confidence level and the alpha level, those are connected. If you actually want to look at the actual confidence interval, if something's outside of a confidence interval, it should be implausible, not a plausible value. It also goes along with a two-sided test. So we have 100 times 1 minus whatever that alpha level, that's your confidence level percent. That would give you 95% confidence interval. It works with a two-sided, and we'll get into more examples that in the future, but one connection I wanted to show you is with these things called Minitab printouts or computer printouts for inferencing. We've done it with linear regression. We've looked at computer printouts from computer programs that do statistical analysis, but this is what it kind of looks like for the other ones with inferencing, and it kind of shows both things. So my example says, what proportion of students are willing to report cheating by other students? Okay, a student project put this question to a simple random sample of 172 undergraduates at a large university. So the question was, you witnessed 2 students cheating on a quiz. Do you go to the professor? The Minitab printout shows the results of a significance test and a 95% confidence interval based on the survey data. Right? So if you look at this, the title does say test and confidence interval for one proportion. That tells us we're doing a 1 proportion z interval or a 1 proportion z test. That name is right there. Maybe I'll show that here. So that's right there. Excuse me. That's whatever the procedures that we're doing. This says test of p equals 0.15 versus p naught equals 0.15. So this is giving our null hypothesis. This is p is not equal to. So this is that how they do it in the computer printout. That's the not equal to. So this then, p is not equal to 0.15 is our h sub 1. That's our alternative hypothesis. So that's given right there. Those are our 2 hypotheses. A couple other notes. I think the example, so I have to change this. The example said 172 and we have 152, so we'll just change that there. But it gives you the number out of the total. So in this case, you can say our p hat, our sample was 19 out of 172. All right, which then gives you what that equals right there. So even more information. And then it gives you a confidence interval. A 95% confidence interval is right here. It's saying that with 95% confidence, the true proportion of this would be between 0.063619 and 0.15, yada, yada, yada. Okay. Now, that's for a confidence interval. This is all for a test. It gives you a z value. And then it gives you the p value. You don't even have to use your table. You don't have to use inverse norm, any of that, or normal CDF, any of that stuff. It's all given. So having a printout does not mean the conditions are necessarily checked. That just means that the numbers were run to get a confidence interval and a z-test. So you would have to go, even with that information, you'd have to go and define the parameter of interest, which hasn't been defined yet, and you'd have to check the conditions. Okay? But the benefit of having this computer printout is most of the rest of the work is already done for you. So let's walk through this. Let's double check. So first of all, our parameter would p equals the true proportion of is it undergrads who would report cheating, essentially. At this university or universities like it. Check the conditions. So we still want to go through, is a simple random sample given? And it does state a simple random sample of 172 undergraduates at a large university. So we do have, random sample of undergraduates that is stated. All right, n times p and n times q. So our proportion that we're trying to look at comes from our hypotheses. So again, this was our null hypothesis. This was our alternative hypothesis. So it's the 0.15. So we're going to use 0.15. It was 172. So I got to change that to a 72. But we would check 172 times 0.15. And we'd check, I guess we can get that value. That's 25.8. We should also check 172 times Q. It's obviously going to be larger. but it is 146.2. So both greater than or equal to 10. So we are check on that one. Last condition is 172 less than 10%. In this case, it's from this large university of all undergrads from this university. We're going to assume yes, because it's at a large university. All right. Now that our conditions happen to all be met, we can go on and actually use this information. So some questions might be like, interpret the p-value, something that we've talked about now. How do you interpret that p-value of 0.146? Not saying a conclusion about it. If there's evidence for anything, what does that p-value mean? So let's go back. We have this nice little fill-in-the-blank template that we've talked about, saying that assuming the true proportion of undergrads at this university who would report cheating is 15%, there is a 14.6% chance of getting a sample proportion of 11%. That's the 19 out of 172. Now I gotta check. Is that value off now? Maybe I should just change 172 to 152 in my example. So what is 19 out of 172? Oh, it is that 0.11. So yeah, just that number is just listed wrong. It is supposed to be 172. So that's the 19 out of 172. You can see that 11% or more extreme. In this case, it could be either side because it's just saying not just by chance in a random sample of 172 undergrads. Okay, that's what it means. Then the follow-up, and also always the end of our statistical analysis, once we have our z-value, once we have our p-value, is to actually give some sort of a conclusion to it. So do these data give convincing evidence that the population proportion differs from 0.15? Justify your answer with appropriate evidence. Well, that's where we want to compare the two. The p-value of 0.146 and whatever our alpha level is. It doesn't give an alpha level. It doesn't actually say that anywhere in this problem, I don't believe. You can go back. I don't think we had it in the problem. So the general consensus is use 0.05. You can use whatever you want, but 0.05 is a very good one to use. So we're just going to say because that's greater than 0.05, we fail to reject the null. Bingo. There's our conclusion. But we want to give some context. So let's say we don't have evidence that the true proportion of undergrads at this university, technically, because we took a sample from this university, who would report cheating? Is different than 0.15. And there's our conclusion. So using a Minitab printout for something like this saves you some time in the long run, but we still want to be able to check all those things. So final follow-up question for this problem. Explain how the confidence interval is consistent with the results of the test from part D, but gives more information than the test. So if you look at it, that 11% that we got from the sample, it does fall in this confidence interval, which means it's plausible. 15% is also, well, that makes sense that it would be there because that's based off of that. I actually want to look at, let's erase that. Our 15% claim. Is 15% reasonable? That's what we're looking at. that falls in there. I mean, it doesn't fall like right in the middle, but it falls in there, and everything in there is equally likely. So I would note something along the lines that 15% is included in the 95% confidence interval. So it is plausible. It is definitely plausible. That doesn't, so there's no reason to believe that it's not the case. The benefit of this is the confidence interval gives an interval of plausible values when the hypothesis test just tells us, allows us to conclude about H naught. So confidence interval gives range of plausible values. But significant test only concludes, oops, concludes about our claim H naught. So there is a benefit to both, but get a little bit more from that confidence interval. So to finish up here, just some logic here. If you're doing a hypothesis test, we're going to pretend like the null hypothesis is true, and we're going to test it out and see if our result is unusual based off of that. It's like considered an outlier. If it is unusual, then the p-value would be less than the alpha, and we would reject the null. If it is not unusual, that means the p-value is higher than that set alpha value, and we would fail to reject anything. We don't have evidence against the null. All right? And that is a great summary of hypothesis testing. And next time we'll get into two-proportion hypothesis testing, and we'll go from there. All right? That is lesson 9.2, part B. We'll see you next time.